All right, so the first thing we're going to introduce, we're talking about polynomial functions. We're going to evaluate them and basically just give some properties. So the standard form, anytime I mention the phrase standard form, this is what it looks like. And I'm going to give it to you generically, so it's going to look a little bit strange, but it looks like this. So we've got f of x, that's always our function notation. So anytime that we say function, you could have this notation here. And this is, again, just your generic form here. Plus, and then you could have however many terms you want in here, and then it's just kind of working its way down, so it looks like this. So this is super, super generic, but just so you know what all these things mean. So all of the A's, every single one, this one, this one, this one, this one, those are real numbers. And then all of these variables here, so you've got x to the n. So n just represents whatever your largest power is. So maybe this is like a 7. This would be x to the 7th, this would be x to the 6th, etc., until you hit x and then just a constant. So n is an integer. So that's important to note that all of those powers are integers. And then two things that we're going to be talking about are the following. First, the degree, which we mentioned this already. The degree of a polynomial is whatever the largest power is. So that's whatever this number is right here. That's the degree. And it's in standard form if it's in descending power order like that. And then this number right here is known as the leading coefficient. That's whatever number is attached to that leading term. Okay, so those are two super important vocabulary words. You can see down here, I'm going to ask you for them. So we are going to evaluate some different types of functions. A constant function, and these are all just going to be examples. So a constant function would be something like 12, literally just a number, and it could be any number that you want. The degree of a constant function is 0, because there's no x term on it at all, so the degree would be 0. In this specific example, the leading coefficient was 12. This is the degree, or this is the term with largest degree, and so it's the leading coefficient. A linear function looks something like this. Something like 4x minus 9. So a linear function has just a power of 1 as its leading term. Whenever you see an x, is technically x to the first. So that's the degree, it's the largest term. The leading coefficient, again, is whatever is attached to this leading term. So here that would be a 4. An example of a quadratic function would be something like this. Okay, so a quadratic is anything with an x squared. So this would be degree 2. The leading coefficient attached to this term would be a 5. Okay, cubic, something like this. Now notice you don't have to have every single term in between. It's just a cubic if this first term is an x cubed. So the degree is 3. The number attached would be an 8. And we can keep going. We can just keep coming up with examples. You've probably heard of these. Maybe Quintic you haven't heard of. It's something to the 4th power. Okay, so something like that would be a quartic. It's got degree 4. In this example, the number attached would be a negative 2. And then a quintic is something with the 5th power attached. So let's just make this one something super simple, because remember, you don't have to have every power in between. So the degree here is 5, and your leading coefficient on this one would be a 6. Okay, so this first example, we'll go really quickly. We're just going to explain whether something is a polynomial in one variable, and then if it is, state the degree and leading coefficient. So this part is very important. We're updating this definition from our previous video. So we've talked about whether things were polynomials before. Now we specifically want them to be polynomials in one variable only. Okay, so this one, yes it is. This is a polynomial in one variable. Its degree is 3. That's the largest exponent. So make sure you're not just looking at the first term. Make sure you're actually looking for the largest degree. And then the leading coefficient is whatever's attached to that term, and that here is a 7. Okay, next example. This one actually isn't even a polynomial in one variable, because you can see we've got 2 variables right there. So this, we'd start with a no here. There are 2 variables. You've got 2 variables, we've got ourselves an issue, because that is no longer a polynomial in one variable. Okay, then this third one, we only have one variable. All the exponents are integers, so we're good on that. The highest power is right here on the end. That's a degree of 6. And then the leading coefficient is whatever's attached to it, and that's a -8. Make sure you actually keep the negative with that. Okay, so that's the first thing that you guys are doing in this first section. The next thing will be evaluating functions. So our first example here, you've got this volume of a respiratory cycle modeled by this function right here, which has some crazy numbers. It says V is the volume, T is time in seconds. Find the volume of air 1.5 seconds into the respiratory cycle. So they're asking us for this. V stands for volume, that's the function that we're using. And then instead of just a T, we're going to plug in T equals 1.5. So when I write this notation like that, the V tells me what function to use, what's in parentheses tells me what to plug in. Okay, so I've done this before in previous sections. I'm literally just going to take this equation, everywhere I see a T, I'm going to plug in a 1.5. So we're just rewriting these equations. Plug in 1.5 for T right here, plus 0.152, plug in 1.5 for T right here, and then our last term. Okay, so you need to make sure you're showing that work. That's what it looks like. So if you write that down, as long as you've got that written down, you can just plug this into your calculator if you wanted to. So I'm just going to plug this in. So we've got negative 0.037 times 1.5, and then to raise to a power, so this little caret key right here, that little up arrow, press that, and then you can insert whatever power you want. Then make sure you arrow over so you're out of the exponent. Plus 0.152 times 1.5 to the second. And I am just plugging this in. Okay, and, oops, there's a glare. That is my decimal approximation. At about 0.477. Okay, and the volume is in liters, so make sure you include your unit since it is a story problem. Okay, next, example 3. We're doing something similar, except this time we're going to be plugging in full expressions instead of just a number. So this is my equation, b, and my variable is m. This expression right here tells me what to plug in. So this b tells me to use this function. What's in parentheses tells me to replace every m with a 2x minus 1. So that's what I'm going to do. I'm going to take this equation right here. Every time I come across an m, I'm going to replace it with 2x minus 1. So 2, okay, there's an m, so we replace it. Plus, there's another m, so we replace it, minus 1. So that's this first part right here. And then minus 3 times b of x. So now I'm going to take this whole function and just plug an x in instead of an m. So it becomes 2x squared plus x minus 1. So there's a lot to simplify from this point. This here is one of the most important things to remember. You do not just square both pieces. It doesn't work like that. We have to write it out twice in FOIL. Okay, we can start cleaning other things up. So plus 2x and then minus 1, so minus 2. And I can distribute this negative 3. Okay, now I'm going to work on foiling this. Don't forget there's a 2 out front. So when I FOIL 2x times 2x, 2x times negative 1, negative 1 times 2x, negative 1 times negative 1. Now I can combine my like terms here. I have a negative 6x squared. I have a 2x minus 3x. And I have a negative 2 plus 3. Okay, so I'm almost done. I'm going to combine these by distributing the 2. This is a negative 4x, so I can distribute the 2 there as well. And then 2 times 1. And I'm going to rewrite these one more time before I combine all my like terms for my final answer. So I have 8x squared minus 6x squared, negative 8x minus x, and 2 plus 1. So this would be my final answer. All right, I've got one more, very similar right here. So h tells me to go to this function right here, and then it tells me what to plug in. Okay, so I'm going into h. Every time I see an x, I'm replacing it with a negative 4d plus 3. Okay, so that's this first part, and then minus 0.5 times h of d. So now I'm just going to plug in a d here. Okay, so I'm going to do the same thing I did here. I can FOIL this out, write it twice in FOIL. Okay, here I'm going to distribute this 5. And here I can distribute this negative 0.5. Okay, here I'm going to FOIL. So I still have that 2 on the outside. Negative 4d times negative 4d. Negative 4d times 3. 3 times negative 4d. 3 times 3. Okay, now I can start combining like terms. So negative d squared. I have a negative 20d and a negative 2.5d. So negative 22.5d. 15 and 3 is 18, minus 1.5 is 16.5. I'm just about there. Distribute this 2. This is a negative 24d, and I can distribute the 2. And then 2 times 9. And finally, I've got all of these terms, and I will be able to combine them all up for my last step. Okay, so 32 minus 1, 31d squared. 48 minus 22.5, so I'm going to have a negative 60.5d, and 18 minus 6.5 would be a 1.5. So that is your lovely final answer.